Hello everybody. I'm going to continue the discussion about quantum mechanics of chapter 8 for general chemistry of Tro. And last lecture we went through wavelength, frequency, amplitude, diffraction, and I'm going to just briefly review whatever I said last time. So we said first thing that we need to know is wavelength, that we show it by lambda. It is unit of meter. And if you choose one, say, wave, and draw that wave. So let's say this one is positive, here is negative, means the phase is positive, phase of the wave is negative, and here we have time. Let's assume this is our wave. Okay. Two identical points on any wave, we call them wavelength, and we show it by lambda. Again, unit is meter. Next one was frequency. We show it by nu, and unit for nu is 1/second or hertz. And what's the frequency? Frequency means number of cycles per second. Okay, so per second. And in this case, I go here, 1 cycle. So I start from here, that's gonna be the start. And the end it will be here. This is 1 cycle. Okay. We say 1 cycle. Okay. Now, how long does it take to pass this cycle? I need to know the time. Let's assume in 1 second. In 1 second, we have only 1 cycle, only 1 cycle past this point. So we say the frequency nu is going to be 1 cycle per second, and it's going to be 1 over second or hertz. How about this position? If 1, and if I go till here, and let's say again, in 1 second, okay? Let's say in 1 second, 2 cycles past this point. So we say in this position, the frequency is going to be 2 cycles per second. Okay, so number of cycles per second. Again, I assume that if we say click on this point and only 1 cycle passed, so I'm gonna say the frequency is gonna be 1/second. Next thing, again, I said if I click on this point and measure how many cycles they are passing us. Let's assume 2 cycles are passing us in 1 second. So in that case, the frequency is going to be 2/second or 2 hertz. Okay. And next one was the amplitude. So again, we have positive, negative. We said distance between 2 identical points, say wavelength, and it is unit of meter, number of cycles per second. So if we click here, 1 cycle in 1 second. That means frequency nu is going to be 1 hertz. Okay. Amplitude This is the amplitude. So we go with amplitude, and show it by A is the distance between maximum point of the wave and the horizontal line, or the minimum point in that line. Okay, call it A. And amplitude is talking about intensity. So we have wavelength, frequency, and amplitude. Okay. Next subject that we reviewed last time, we said we have this formula, C equal to lambda multiply frequency. C is the velocity of light, and it's equal to this number. Okay, next. Okay. We said wavelength, it has unit of meter, frequency, 1/second. And we know C, it comes with meter over second. So meter multiply 1/second is going to give us meter over second. And let's call this one first formula. And the second formula is energy equal to h nu. Okay, energy is equal to h nu. What's the h? H is the Planck constant. And nu is the frequency. Has unit of 1/second. This one is joule. Okay. So h must be joule multiply second. So then you cancel second by second, and you will get joule, which is the right unit of energy. What's the number for h? Is 6.626 multiply 10 to the power of minus 34 joule to second. Okay, joule to second. And call it number 2 formula. Okay. If you merge 1 and 2, you get new formula. So we have 1 equal to C lambda multiply frequency. Frequency is going to be C over lambda. And the second formula was energy is equal to h nu. So nu is going to be equal to E over h. E over h. I can calculate the frequency either through that one or this one. Okay. And I can, again, I said I can merge them. Wherever I have frequency in second formula, I will replace it by C over lambda. So the third formula, feed the second by first formula. Energy is going to be equal to H multiply nu. Get the nu from first formula. It's going to be C over lambda. We get HC over lambda. HC over lambda. Nice thing with this formula, numerator, H multiply C, both are constant. Both of them are constant. The only variable we have is just lambda. Okay. Energy inversely connected to lambda. Well, there, energy was directly connected to frequency. So now let's talk about the relationship between energy and wavelength and energy and frequency. Okay. First, wavelength. What will happen if wavelength goes up? So what will happen with the frequency if wavelength goes up? Okay, so first case, if wavelength goes up, then nu has to go down. Why? C equal to lambda multiply frequency. Frequency is going to be C over lambda. C is constant. If this one, if wavelength goes up, then the frequency has to go down. Okay. If C goes up, if lambda goes up, then the frequency has to go down. Next thing, again, we're talking about lambda. We have energy equal to hc over lambda. We said these two are constant. If wavelength goes up, then energy will go down. And last thing is the frequency. What will happen with energy when frequency goes up or down? So I'm going to separate this one. We have energy is equal to h nu, h constant. So h is constant. Nu. If nu goes up, then energy, it will go up. Okay, so energy directly connected to frequency, energy inversely connected to wavelength. Okay. If this one goes up, then energy it will go up. If wavelength goes up, energy it will go down. Frequency inversely connected to wavelength. If wavelength goes up, frequency it will go down. Okay, and then mention it here. So I went through the formulas, and next subject that we went through it, we said Niels Bohr mentioned that when you talk about any atom, the atom is made of nucleus, that it has protons in it, and then you will have orbits around that nucleus. Okay. Inside the nucleus we have protons and neutrons, and inside any of these orbits, I'm gonna call them here orbit, we like as I said, the nucleus, we have protons or neutrons, and anywhere here on this orbit there is a chance to find electron, or these orbits are the place that electrons are using to hang around the nucleus. So electron can hang around the nucleus on this orbit. So let's say there. So electron is going to hang around nucleus, and all the time nucleus is pulling it down, because the nucleus, it has positive charge, and electron it has negative charge, so there is electrostatic interaction between them. And because this one is moving so fast, or has to move fast enough to not fall inside the nucleus. And he said, like first orbit, I'm going to call it, or I'm going to show it by n equal 1, second orbit n equal 2, and the third one n equal 3. You want to find energy of electron that's hanging around the nucleus on n equal 1 or first orbit. You will use this formula. Energy of orbit number n is going to be equal to minus RH multiply 1 over square of n. Okay, square of n. So energy for electron that belong to, let's say, second or third, let's go with the third orbit, n is equal to 3, you say 3 is going to be equal to minus RH, and it says 1 over square of n. What's the n? Any orbit you're talking, any n you're talking, and it will be 1 divided by 3 to the second. Okay. And what's the RH? RH is a Rydberg constant. So I'm going to say it here. RH, Rydberg constant. Okay. And RH is equal to 2.18 multiply 10 to the power of minus I believe 28 joule. Okay, 2.18 multiply minus 28 or 18. Please give me a second. I think I made a mistake here. I believe it was minus. It can be minus 18. Sorry, minus 18, not 20. Yeah, minus 18. Yeah, minus 18 joule. Okay, so 2.18 multiply 10 to the power of minus 18 joule. Sorry about this one. Okay, I think I need to drink coffee. And you know that I'm so addicted to coffee, and I did not drink mine today. Okay. So, energy of any electron, you can find it by knowing orbit of that electron. So we can use this formula to find energy of the electron. Just give me n, and then I can calculate the energy. We're talking about, this is the nucleus, n equal 1, and that's going to be n. This one is going to be n equal 2. So for electrons that belong to n equal 1, n equal 1, energy is going to be minus RH multiply 1 over 1 to the second, and it's going to be just minus RH. Okay. How about n equal 2? It will be minus RH 1 over 2 to the second is going to be minus RH divided by 4. Okay. Now, I want to talk about the change with energy when one electron is moving up or down. I want to calculate that one and see what will happen. So let's assume we have one electron that's sitting in N1 here, this electron, and we want to shoot the electron to N2. We want to send it to N2. So from N1 to N2. From N1, we want to send it to N2. And we want to calculate the change with the energy. Change with energy is going to be energy of second level minus energy of the first level. So delta E, we got it minus RH divided by 4 minus RH, okay, for the first one. And you can put 1 here as a denominator, or just keep it that one. So it will be minus RH over 4 plus RH. That's the change in energy when you send electron from N1 to N2. Okay, it's kind of weird, and there should be a way to make it easy, to calculate the change with energy. I don't want to deal just with RH. I'm going to say energy for second level, I can find it through this formula. 1 divided by 2 to the second. I'm using this formula. Okay. And energy for the first level is going to be minus RH 1 divided by 1 to the second. Let's subtract them. Delta E is going to be E2 minus E1. E2 is minus RH multiply 1 divided by 2 to the second. Okay. Next one, minus RH 1 divided by 1 to the second, and I close it. I'm going to get factor from RH. It will be minus, let's get minus RH, minus RH. From first one, we will have here, from this one, if we get the minus RH out, we will have 1 over 2 to the second minus, from the second one, we got minus RH out, so we will have 1 divided by 1 to the second. How did I get this one? Delta E is equal to minus RH 1 multiply 1 over, what's this one? N2. Okay, this is N2. So let's say N2 minus N1 to the second. So from now, I'm going to use this formula to calculate change in energy when I sending one electron up or down. Okay, when I say up, I mean up level or lower level. So we go delta E, change with energy is going to be equal to minus RH multiply 1 final N, okay, final N to the second minus 1 over initial N to the second. Okay, final N to the second, initial N to the second. And RH is equal to 2.18 multiply 10 to the power of minus 18 joule. You have energy is equal to H nu, energy is equal to Hc over lambda, and C is equal to lambda multiply frequency. You will use all these three formulas to calculate, for example, nu, or calculate, wavelength. Okay. Before I jump and do, the calculation, I need to talk about absorption versus emission. Let's say we have one electron that's sitting in n equal 3. And we want to send the electron to n equal to 5. So here is our electron. We want to shoot the electron to a higher level. In order to do it, we need to give it energy. Otherwise, it's not going to go up. So this electron is not going to go up. So I'm going to give it some energy. I will give this electron energy and it will go up. So we are adding energy, which is equal to H nu. So we are adding energy to this electron that belongs to n equal 3, and it will go higher level. So I have the right to say energy of the electron when here is going to be higher than energy of the electron when it's sitting lower level. So energy at the end is higher. energy at the end is higher than the starting point because we are adding energy to the electron. We are adding energy to this electron. So when I say energy, I mean energy of electron is going to be higher. Okay. We gave energy to the system, so the system absorb energy. Sorry, the system absorb energy. We call this one. We call it absorption. We call it absorption because our system got energy. Our system absorbed energy. Okay. So now write this one. Write the delta E. Delta E equal to minus RH multiply 1 over final n. This is going to be the final. And this one is going to be the initial. 1 divided by 5 to the second minus 1 over 3 to the second. Now you need to see whether this one is a positive or negative. 1 over 5 to the second is smaller than 1 over 3 to the second. So when I subtract them, answer for this part is going to be negative number. Negative to negative, it will give you a positive answer for delta E. Positive answer for delta E. So now we got energy is equal to delta E, or energy is equal to H nu. We got the energy positive. Energy is positive. H is a positive number and the frequency is positive number. So that's perfect. Lucky us. We don't need to do anything more. We can calculate the frequency. The frequency is going to be E, a positive number, divided by H, which is a positive number. And it's going to give us the right answer. Remember, frequency is number of cycles per second. Frequency cannot be 0. Frequency can be 0, but then it will go up. You go with, let's say, you start with 0 and slowly you increase the number. But the frequency cannot be negative. So what will happen if this one is negative? If it's negative, if the final answer is negative, then something is wrong here and we need to fix it. So for now, anytime you start with lower level of energy or lower N, lower level of energy, this is going to be the initial point. Let's say we start with 2 and we send it to N equal to 3. You need to apply energy. We are adding energy. Because we are adding energy, this system is absorbing. Okay, absorbing in it. So you are dealing with absorption. Okay, I will ask about this one. Okay. Next, what if electron is going down from higher level is going to lower level? N equal to 5. This is going to be the initial point. And I'm going to send the electron to N equal 3. And this is going to be the final point. So here is our electron. Electron is going down. when electron is going down, has to give up some energy. So it's going to give you some energy. It will emit that energy. So emits energy. This time we say we are dealing with emission. Okay, we are dealing with emission. We are sending photons out. Okay, we are sending photons out. Okay, I want to calculate the energy of that photons. How much energy I'm shooting out. Okay. I go with delta E minus RH multiply 1 over initial final n. Final n to the second minus 1 over initial n to the second minus RH 1 over initial n, in this case is going to be 5. Don't say 3 because the 3 is a smaller. Okay, I don't know, like, yeah, again, don't say you know, like the, I don't know what I said actually, sorry about it. So the initial is going to be 5. Initial is 5. Don't say 3 n equal 3 is the initial one because it's a smaller. That's not true. Okay, the starting point. Starting point. It will tell you the initial n. Okay, and this one is the final point or the destination. So I go with 1 over n to the final n to the second. Final n is 3 to the second minus 1, 5 to the second. 1 over 3 to the second is bigger than 1 over 5 to the second. So that means this number will be positive. And now we have a problem because minus multiplied plus, it will be negative. So we got delta E equal to a negative number. Energy is equal to H nu. H is a positive number. And if nu is negative, then frequency will be negative number divided by a positive number. It will give you a negative number for frequency, and that's wrong. Okay, this is wrong. Okay, so whenever you are dealing with emission, you need to fix this problem, and the way you fix it, you treat the atom as a system. So I'm going to say I'm dealing with atom. N equal 3. Electron is going down, is giving us energy equal to H nu. Okay. Now you will treat this, which is the atom, you treat it as a system. And this one is going to outside. Or it will be taken by environment. So we're going to say change with energy of the system, which is the atom, change with energy of the system or atom is going to be equal to minus change with energy of outside. So change with energy of the system is going to be equal to minus change with energy of outside or surrounding. outside or surrounding. And now you treat this, treat this one, as I said, as a system, and it's your atom. So you say change with energy of the atom is going to be equal to minus change with energy of outside, which is equal to energy of the photon. Equal to energy of the photon. So I will use this one to calculate the energy of the photon. Remember, this one change with the energy here, change with energy of the atom is going to be negative. This one, it will be a negative number. So you say energy of change with energy of outside, or energy of the photon, change with energy of outside, which is equal to energy of the photon, is going to be equal to minus change with energy of the atom. So it's going to be equal to minus change with energy of the atom. And energy of the atom, it will be a negative number. So now negative to negative, it will be positive. Energy is positive. And that's perfect. Hallelujah. Okay. Let's practice one question about it, and then you will see how to use this fact. Okay. And I go with this. N equal 5, and I shoot it down to n equal 3. It will give us energy. Let's calculate frequency of the photon. Let's calculate this one. What's the frequency of this photon that was emitted by electron transfer from N5 to N equal 3? We go with delta E for the atom equal to minus RH 1 over final N to the second minus initial N to the second. So it's going to be delta E equal to minus 2.18 multiplied 10 to the power of minus 18 joule for RH, multiply 1 over initial N, 3 to the second minus 5 to the second. There is no unit for this term except the joule for Rydberg. So your final answer, it will have unit of joule. Let's get this one. So we have 1 divided by 9 minus, 1 divided by 9 minus 1 divided by 25. That's going to give us 0.07 multiply 2.18 power of minus 18. I got the number minus 1.55. So delta E of the atom is minus 1.55 multiply 10 to the power of minus 19 unit joule. Look at this one. We got the energy negative. And as I said, we need to fix it. Okay. We got the energy negative, so we need to fix it. And the way we fix it, we're going to use this fact. That delta E for the system is equal to minus delta E of the outside. Delta E of the system is going to be equal to delta E of the atom, and is equal to this number. So let's move forward and calculate frequency. So we go with this. Delta E of the atom equal to delta E of the system. And delta E of the atom, we just got it. We just got it equal to minus 1.55 multiplied 10 to the power of minus 19. So I write it here, minus 1.55 multiplied 10 to the power of minus 19 joule. And delta E of outside or surrounding is equal to energy of the photon, because that energy is going out. The energy is going out, and it's going to be the one that will be added to outside. So I can say whatever outside is gaining, it will be equal to whatever the photon is bringing with itself. So change with energy of outside is going to be equal to whatever coming from the atom to the outside. Okay, so delta E of the system equal to minus delta E of outside, delta E of the atom equal minus delta E of outside equal to energy of the photon. So now energy for the photon, or delta E of outside, equal to minus delta E of the atom. So energy of the photon, delta E of the outside, equal to minus of minus 1.55 multiplied 10 to the power of minus 19 joule. Now we have it positive. It's going to be plus 1.55 multiplied 10 to the power of minus 19 joule. Okay, so now we got energy of the photon equal to a positive number. Now we can calculate the frequency of this photon. So always you need to do this adjustment when it comes to energy. So now you go with energy of photon equal to plus 1.55 multiplied 10 to the power of minus 19 joule, and energy is equal to h nu. So nu is going to be equal to E over h divided by h. You cancel joule by joule, and we get 1 over second, which is the right unit of frequency. So I will divide this one by 6.626 power of minus 34, and I got this one equal to 2.34 multiply 10 to the power of 14. Unit is 1 over second or hertz. Okay, let's double check it. 1.55 to the power of minus 19 divided by 6.626 of minus 34. 2.34 multiply 10 to the power of 14, 1 over second or hertz. And now frequency is a positive number, not negative, and that can be correct.